built-in fuses used to prevent overload in specialized systems are often called heaters due to their operating principle. These devices are designed to protect systems from damage by interrupting the flow of current when an overload condition occurs. The term heaters arises from the fact that these fuses heat up when subjected to excessive current. This heating is a critical part of their function, leading to the eventual blowing of the fuse and the cessation of current flow. While heaters is a general term, the specific names for these fuses can vary depending on a particular system and application. Some common names include thermal fuses, thermal cutouts, thermal links, and resettable fuses. These variations reflect the different designs and functionalities of the fuses while still adhering to the fundamental principle of heat-induced interruption. Thermal fuses are designed to blow when a specific temperature is reached. This temperature is predetermined based on the fuse's construction and the materials used. When the current exceeds the fuse's rated capacity, the increased current flow generates heat within the fuse element. As the temperature rises and reaches the critical point, the fuse element melts or undergoes a structural change that causes it to break the circuit. Thermal cutouts are similar to thermal fuses in that they rely on temperature to trigger their operation. However, thermal cutouts often involve a more complex mechanical or chemical mechanism. For example, some thermal cutouts use a bimetallic strip that bends when heated. This bending action can trigger a switch or release a spring-loaded contact, interrupting the circuit. Thermal links are another type of thermal fuse. These devices typically consist of a fusible link surrounded by a thermal insulation material. When the temperature rises to a critical level, the fusible link melts, causing the circuit to open. The insulation material helps to prevent the heat from dissipating too quickly, ensuring that the fuse operates reliably even under rapidly changing temperature conditions. Resettable fuses, also known as positive temperature coefficient devices or polyfuses, offer a different approach to overload protection. These fuses do not blow in the same way as traditional fuses. Instead, they increase their resistance dramatically when overheated. This increase in resistance limits the current flow, protecting the circuit from damage. Once the overload condition is removed and the fuse cools down, its resistance returns to a normal level, and the circuit can resume operation. Resettable fuses are often used in applications where temporary overloads are common, and it is desirable to avoid the need to replace a blown fuse. The underlying principle behind the operation of heaters and their various subtypes is based on Joule's law, which states that the heat generated by a conductor is proportional to the square of the current, the resistance of the conductor, and the time for which the current flows. Mathematically, this is expressed as heat equals I squared RT, where I is the current, R is the resistance, and T is the time. When a circuit is operating under normal conditions, the current flow is within the designed limits, and the heat generated is dissipated without causing any damage. However, when an overload occurs, the current increases significantly. This increased current leads to a much greater amount of heat being generated in the fuse element. The fuse element is designed to have a specific melting point or trigger temperature. When the heat generated exceeds the ability of the fuse to dissipate it, the temperature rises rapidly until it reaches the critical point. At this point, the fuse element melts, breaks, or undergoes a structural change that interrupts the circuit. The design of heaters and their subtypes involves careful consideration of several factors, including the current rating, the voltage rating, the operating temperature, the response time, and the physical dimensions. The current rating specifies the maximum amount of current that the fuse can carry without blowing under normal operating conditions. The voltage rating specifies the maximum voltage that the fuse can safely interrupt. The operating temperature specifies the range of temperatures within which the fuse will function reliably. The response time specifies how quickly the fuse will blow when overload occurs. The physical dimensions of the fuse must be compatible with the system in which it is used. The materials used in the construction of heaters are also carefully selected to ensure reliable operation and to meet safety standards. Common materials include alloys of tin, lead, zinc, copper, and silver. These materials have specific melting points and electrical conductivity properties that make them suitable for use in fuses. The selection of materials also depends on the specific application and the desired performance characteristics. In addition to protecting against overloads, heaters and their subtypes can also protect against short circuits. A short circuit occurs when there is a direct connection between 2 points in a circuit that have different voltage potentials. This can result in a very high current flow, which can quickly damage equipment and pose a fire hazard. Fuses are designed to interrupt the current flow quickly in the event of a short circuit, preventing further damage. The installation and maintenance of heaters are critical to ensure their proper operation and to maintain the safety of the system. Fuses should be installed in accordance with the manufacturer's instructions and applicable electrical codes. It is important to use the correct type and size of fuse for the application. Replacing a fuse with one that has a high current rating can be dangerous because it may not provide adequate protection against overloads or short circuits. Fuses should be inspected regularly for signs of damage or corrosion. Blown fuses should be replaced immediately with new fuses of the correct type and size. In some cases, it may be necessary to troubleshoot the circuit to determine the cause of the blown fuse before replacing it. This can help to prevent the problem from recurring. Furthermore, understanding the various standards and regulations governing the use of fuses is important. Organizations such as the National Electrical Manufacturers Association, or NEMA, and the International Electrotechnical Commission, or IC, publish standards for fuses that specify their performance characteristics and safety requirements. Compliance with these standards helps to ensure that fuses are safe and reliable. The National Electrical Code, or NEC, also provides guidelines for the installation and use of fuses in electrical systems. Understanding and adhering to these guidelines is essential for ensuring the safety of electrical installations. In summary, heaters is a general term for built-in fuses that protect specialized systems from overload by heating up and interrupting the current flow. While the specific names for these fuses may vary, they all function based on the principle of heat-induced interruption. Understanding the different types of thermal fuses, their operating principles, and their installation and maintenance requirements is crucial for ensuring the safety and reliability of electrical systems. Consider a scenario where a motor in a manufacturing plant is drawing excessive current due to a mechanical fault. Without proper overload protection, the motor windings could overheat and burn out, resulting in costly repairs and downtime. A heater, specifically a thermal overload relay, would detect the excessive current and trip the circuit, shutting down the motor before any damage occurs. This prevents the motor from being damaged and also protects the rest of the electrical system from being overloaded. Another example could be a power supply in an electronic device. If the power supply is subjected to an overvoltage condition, it could draw excessive current. A heater, such as a thermal fuse, would blow and prevent the power supply from being damaged and potentially causing a fire. These examples highlight the importance of using heaters to protect electrical and electronic systems from damage. The use of heaters is not limited to industrial or commercial applications. They are also used in residential settings to protect appliances, lighting circuits, and other electrical equipment. For instance, a thermal fuse in a clothes dryer prevents the dryer from overheating and potentially causing a fire. In a home entertainment system, a resettable fuse protects the speakers from being damaged by excessive volume levels. The proper selection and application of heaters require careful consideration of the specific requirements of the system being protected. Factors to consider include the current rating, voltage rating, operating temperature, response time, and physical dimensions of the fuse. It is also important to understand the potential hazards that the system may be exposed to, such as overloads, short circuits, and overvoltages. By carefully considering these factors, it is possible to select the appropriate heater to provide reliable and effective protection. The term heater can also refer to other types of thermal protection devices, such as thermistors and bimetallic strips. These devices are not fuses in a traditional sense, but they provide similar functions by responding to temperature changes and interrupting the circuit or reducing the current flow. Thermistors are semiconductor devices that change their resistance with temperature. They can be used to sense temperature and to provide overload protection. Bimetallic strips are made of two different metals that have different coefficients of thermal expansion. When heated, the strip bends, which can be used to actuate a switch or other mechanism. In conclusion, while heaters is a general term, it is important to understand the specific types of thermal protection devices that are available and their operating principles. By selecting the appropriate device for the application, it is possible to provide reliable and effective protection against overloads, short circuits, and other electrical hazards. Now let's delve further into the technical aspects of these protective devices. Firstly, consider the interrupting rating. This is the maximum fault current a fuse can safely interrupt without failing. It's crucial to select a fuse with an interrupting rating that exceeds the maximum potential fault current at its installed location. Secondly, the ampere rating is the continuous current a fuse can carry without opening. Select an ampere rating appropriate for the circuit's normal operating current, typically 125% of the continuous load, to prevent nuisance tripping. Thirdly, the voltage rating must be equal to or greater than the circuit voltage. Using a fuse with a lower voltage rating can lead to arcing and potential failure. Fourthly, the time current characteristics describe how quickly a fuse will open under overload conditions. Different fuse types offer varying time current curves, such as fast acting for sensitive electronics or time delay for motor starting applications. Fifthly, the temperature rating is essential as fuse performance can be affected by ambient temperature. Consult the manufacturer's datasheet for temperature rating curves to ensure proper fuse selection in high-temperature environments. Sixthly, consider fuse standards such as Underwriters Laboratories or UL and IEC standards ensure fuse safety and performance. Compliance with these standards is critical for product certification and regulatory compliance. Seventhly, the physical size and form factor. Fuses come in various sizes and shapes to fit different fuse holders and equipment. Select a fuse with the correct dimensions to ensure proper installation and operation. Eighthly, the fuse holder compatibility is important. Use fuse holders that are specifically designed for the type of fuse being used. Improper fuse holders can compromise fuse performance and safety. Ninthly, the environmental conditions must be considered. Fuses used in harsh environments, such as those with high humidity or corrosive atmospheres, may require special coatings or enclosures to prevent degradation. And 10th, the agency approvals must be obtained. Ensure that the fuses are approved by relevant regulatory agencies such as UL, Canadian Standards Association, or CSA or IEC for use in specific applications and regions. The selection of appropriate heaters and fuses is directly tied to electrical safety standards outlined in codes like the NEC. For example, NEC Section 240.4 addresses the protection of conductors against overcurrent, specifying that conductors must be protected in accordance with their ampacities. Fuses and circuit breakers are the primary means of providing this protection. NEC Table 310.15, formerly 310.16, provides ampacity ratings for various conductor types and sizes, which are essential for selecting the correct fuse size. Furthermore, NEC Section 430 covers the protection of motors, specifying different requirements for motor overload protection and short circuit protection. Heaters, in the context of motor starters, are often used as overload relays, providing protection against sustained overcurrent conditions that could damage the motor. The NEC provides specific guidelines for selecting the appropriate heater size based on the motor's full load current and service factor. In addition to the NEC, other industry standards, such as those published by NEMA and IEE, provide guidance on the selection and application of fuses and other protective devices. These standards often include detailed information on fuse characteristics, coordination studies, and best practices for electrical system design. Proper coordination of fuses is critical to ensure that only the faulted portion of the system is de-energized during an overcurrent event. This involves selecting fuses with appropriate time current characteristics to allow downstream fuses to clear faults before upstream fuses operate. Coordination studies are typically performed using specialized software tools to analyze the performance of different fuse combinations under various fault conditions. The maintenance and testing of heaters and fuses are also important aspects of electrical safety. Regular inspections should be performed to identify any signs of damage, corrosion, or overheating. Fuses should be tested periodically to verify their proper operation. This can be done using a fuse tester or by measuring the voltage drop across the fuse while it is carrying current. If a fuse is found to be defective, it should be replaced immediately with a fuse of the same type and rating. In addition to physical inspections and testing, electrical systems should be subjected to periodic insulation resistance testing to identify any potential insulation faults. Insulation resistance testing involves applying a high voltage to the conductors and measuring the leakage current. Low insulation resistance can indicate damaged insulation, which could lead to short circuits and other electrical hazards. The results of insulation resistance testing can be used to identify areas where repairs or replacements are needed. Electrical safety training is essential for all personnel who work on or near electrical equipment. Training should cover topics such as electrical hazards, safe work practices, lockout-tagout procedures, and the proper use of personal protective equipment. By providing adequate training, employers can help to ensure that their employees are aware of the risks associated with electricity and that they know how to work safely. In conclusion, the selection, installation, maintenance, and testing of heaters and fuses are critical components of electrical safety. By following industry standards, implementing proper safety procedures, and providing adequate training, it is possible to minimize the risk of electrical hazards and to ensure the safe and reliable operation of electrical systems. The proper application of heaters and fuses not only protects equipment and personnel, but also contributes to the overall efficiency and reliability of electrical systems. By preventing damage from overloads and short circuits, these protective devices help to minimize downtime and reduce maintenance costs. In addition, the use of energy-efficient fuses can help to reduce energy consumption and lower operating expenses. For example, some fuses are designed with low resistance to minimize energy losses due to heat generation. These fuses can help to improve the overall efficiency of the electrical system and reduce the environmental impact. Furthermore, the use of advanced fuse technologies, such as solid-state fuses, can provide even greater levels of protection and performance. Solid-state fuses use electronic components to sense overcurrent conditions and to interrupt the circuit. These fuses offer faster response times, higher interrupting ratings, and greater reliability compared to traditional fuses. They are also less susceptible to damage from vibration, shock, and temperature variations. The integration of smart fuse technologies into electrical systems can provide real-time monitoring of fuse status and performance. This information can be used to identify potential problems before they lead to failures and to optimize the operation of the system. For example, smart fuses can provide alerts when a fuse is approaching its end of life or when it has been subjected to an overcurrent event. This allows for proactive maintenance and prevent unexpected downtime. In addition to protecting against overcurrents, heaters and fuses can also be used to protect against other electrical hazards, such as ground faults and arc faults. Ground faults occur when there is an unintentional connection between a conductor and ground. Arc faults occur when there is an electrical arc between two conductors or between a conductor and ground. Both ground faults and arc faults can cause fires and pose a serious safety hazard. Ground fault circuit interrupters or GFCIs are used to protect against ground faults. Arc fault circuit interrupters, RFCIs, are used to protect against arc faults. These devices are designed to detect the presence of ground faults and arc faults and to quickly interrupt the circuit, preventing fires and other hazards. In summary, heaters and fuses are essential components of electrical safety and play a critical role in protecting equipment, personnel, and property from electrical hazards. By understanding the different types of fuses, their operating principles, and their application requirements, it is possible to design and maintain safe and reliable electrical systems. The continuous advancement of fuse technologies is providing even greater levels of protection, performance, and efficiency, contributing to a safer and more sustainable electrical infrastructure. Let's expand the discussion further by introducing some specific fuse types and their applications. Firstly, there is the cartridge fuse. These are cylindrical fuses commonly used in automotive, electronic, and appliance applications, offering a wide range of voltage and current ratings. Secondly, blade fuses are typically used in automotive applications, featuring a plastic body with exposed blade terminals for easy installation and replacement. Thirdly, plug fuses, also known as Edison-based fuses, are older types commonly found in residential electrical panels, gradually being replaced by circuit breakers. Fourthly, time delay fuses are designed to withstand temporary overloads, such as motor starting currents, without opening, making them suitable for inductive loads. Fifthly, fast-acting fuses open very quickly in response to overcurrents, providing superior protection for sensitive electronic components. Sixthly, semiconductor fuses are specifically designed to protect semiconductor devices, such as diodes and transistors, offering extremely fast response times and low let-through current. Seventhly, high rupture capacity or HRC fuses are designed to safely interrupt very high fault currents, commonly used in industrial and commercial power distribution systems. Eighthly, resettable fuses, also known as polymeric positive temperature coefficient or PPTC devices, increase their resistance dramatically during an overcurrent event, limiting current flow and resetting automatically when the fault is cleared. Ninthly, surface mount fuses are miniature fuses designed for surface mounting on printed circuit boards, commonly used in portable electronic devices. And 10th, Class CC fuses are compact, high-performance fuses used in control panels and other industrial applications, offering excellent current-limiting capabilities. When selecting a fuse, it's important to consider the coordination with other protective devices in the system. Fuse coordination ensures that only the fuse closest to the fault opens, minimizing disruption to the rest of the system. This involves selecting fuses with appropriate time current characteristics so that downstream fuses clear faults before upstream fuses operate. In addition to fuse coordination, it's also important to consider the selectivity of fuses. Fuse selectivity ensures that the fuse with the lowest ampere rating opens first in response to an overcurrent event. This helps to isolate the fault and prevent unnecessary tripping of other fuses in the system. Proper fuse selectivity requires careful consideration of the ampere ratings and time current characteristics of all fuses in the system. The installation and maintenance of fuse holders are also important for ensuring the reliable operation of fuses. Fuse holders should be installed in a clean, dry environment and should be protected from physical damage. The fuse holder contacts should be cleaned periodically to remove any corrosion or debris that could interfere with the electrical connection. When replacing a fuse, it's important to use the correct type and rating of fuse. Using a fuse with a higher ampere rating can be dangerous because it may not provide adequate protection against overcurrents. Using a fuse with a lower ampere rating can cause nuisance tripping. It's also important to ensure that the fuse is properly seated in the fuse holder. A loose fuse can overheat and cause a fire. In addition to visual inspections, fuses should be tested periodically to verify their proper operation. A simple continuity test can be performed using a multimeter to check that the fuse is intact. More advanced testing methods can be used to measure the fuse's time current characteristics and verify that it meets its specifications.